It's time now. So let us start on time. And today's Professor Samir Chavan is the today's talk speaker, and he's going to talk about the Dirichlet-type spaces on the unit ball and the joint two isometries.
Yeah. Okay. So thanks, Surjit. So I hope everyone can hear me. And so let me start thanking Sayan and Srijan for this wonderful opportunity. And so this talk is about Dirichlet-type spaces, and it has roots in operator theory. So the motivation comes from operator theory, and the initial work in one variable has been done by Stephen Richter. So I'll not start with the operator theoretic part, but what will if time permits, then maybe towards the end we'll try to come back to operator theory. So let me, because this is I kept the talk for broader audience, and let me start with the vocabulary of the talk. Okay, so there are some because what we are going to do, we are trying, so it's an ongoing work, and this is a joint work with Rajiv Gupta and Ramiz Reza, MT Ramiz Reza. So we tried to get or find multivariable counterpart of Richter's theory. Okay, and Richter's theory is about Dirichlet-type spaces on unit disk. So one multivariable counterpart is ball case, and one is polydisk. Polydisk we are not discussing in this talk. So let's, for ball case, we need some vocabulary from the famous monograph by Rudin, which is function theory on the unit ball. So what we need is a little part of that monograph, but let me recall few definitions. So this BD denotes the unit ball in CD, and this norm Z norm is a Euclidean norm, and then the sphere is denoted by del PD. And phi a, we have not, I have not written the explicit expression, but phi a is an automorphism of the unit ball which maps 0 to A. Okay. Now there are two analogs of Poisson kernel for the unit ball, and these are distinct in dimension bigger than equal to 2. In t equal to 1, you can easily see that the first analog is invariant Poisson kernel, so which is denoted by pi, and the second is the Euclidean Poisson kernel, which is denoted by pe. And you can see that this pi and pe both are same in dimension d equal to 1. Okay, and we'll see that these two in higher dimensions, these two, although they have many common properties, there is one unique or essential feature where they differ. Okay, and that is the harmonicity. So let me move to the, so we need this because I'm not going to use the explicit expression, but you can just keep in mind the difference. Okay, so the difference is you will see that this pi is somehow because we have used the inner product. Okay, and here in P we have used the difference of Z and zeta. Zeta is coming from the boundary. And let me move to the next slide, and we'll try to understand what is the difference between Pi and Pe. Okay, so before we see the difference, let's define another object which is called Poisson integral. So you take P to be either invariant Poisson kernel or Euclidean Poisson kernel, and you fix a measure, finite or positive Borel measure on the unit sphere, and you integrate the Poisson kernel with respect to this measure over the sphere. Okay, so because P is a function in Z and zeta, and we are integrating with respect to zeta, the right hand side is a function of Z. Okay, and it's a function defined on the open unit ball. Now, so to understand that how this Poisson kernel, invariant Poisson kernel and Euclidean Poisson kernel, they are distinct. One way is that you focus on Poisson integral, and if you take the Poisson kernel to be Euclidean Poisson kernel and you look at the Euclidean Poisson integral, then it is always harmonic. So one way to see this is explicit calculation, or you can appeal to the mean value property. So here, let me recall what is the Laplacian. It's a usual Laplacian, and the expression is given. We have added 4 just for, so this is for calculation purpose. So now let's look at the invariant counterpart or invariant Laplacian. So invariant Laplacian is delta tilde, and it is defined. So if you recall that we denoted this the automorphism of the unit ball, which maps z to 0 by phi z. So if you take that phi z and you compute the so the invariant Laplacian is of f at z is precisely the usual Laplacian of f composed phi z evaluated at 0. And you can write down the explicit expression. So here delta ij is the Kronecker delta. So delta ij equal to 1 if I not equal to j, and I equal to j, and it is 0 otherwise. And now this invariant Poisson integral, it has a property which is called Mobius harmonic, means it is a solution of the invariant Laplacian. So now it is to be noted that in dimension bigger than or equal to 2, this invariant Poisson integral cannot be harmonic. So this is not obvious, but so there could be a direct verification also, but it may be deduced from an old result by Rudin, which says that if a function is, if you take a function on the unit ball, which is real valued, and suppose it is harmonic as well as Mobius harmonic, then it has to be a real part of a holomorphic function. Okay, so it is necessarily real part of the holomorphic function. Now you can easily see that these are non-negative functions, so they cannot be real part of holomorphic function on unit ball. So we can conclude that this pi mu, or the invariant Poisson integral, is Mobius harmonic if and only if d is equal to 1. In case d equal to 1, you will see that this Euclidean Poisson kernel, Poisson integral and invariant Poisson integral both agree, because the corresponding Poisson kernel, they are same. Now, so what we are going to, so the essential idea in studying Dirichlet-type space, or in our approach to Dirichlet-type space, to the study of Dirichlet-type space, is based on harmonicity. Okay, so we are going to exploit the Dirichlet problem, and you'll see that since this invariant Poisson integral doesn't have harmonicity, you'll see that the analog of Richter's theory, which I have not explained, but we'll come to that, fails. And so it's a formula which allows you, which provides a powerful tool to study the Dirichlet-type spaces. So we are going to study Dirichlet-type spaces. So there are 3 problems. So first is that, so it's a function space in several variables, say z1, z2, zd, and it's a function space of holomorphic function. And the natural questions are, what are the multipliers, whether polynomials are dense, and so on. Okay, so these are the issues we are going to discuss. Let me now move to the next slide, and so this is what I explained. this invariant Poisson integral is harmonic if and only if d equal to 1. Now we want to we give the definition of Dirichlet-type space. So roughly it is a subspace of closed subspace of the Hardy space, and the norm given on the Dirichlet-type space is you have to take the, of course you have to take the Hardy norm, and you have to add to the Hardy norm, you have to add the norm which is weighted L2 norm of the gradient of f. Okay, and so the weight being the Poisson integral. So if you take Euclidean Poisson integral, you can call it Euclidean Dirichlet-type space, and if you take invariant Poisson integral, then you'll get invariant Dirichlet-type space. Now there are some difficulties in studying invariant Dirichlet-type space. So and probably one may think that this gradient may not be a good choice for defining invariant Dirichlet-type space. In place of gradient, you can try invariant gradient. So you can see that in several variables there are various possible definitions of Dirichlet-type space. So however, one can see that if you replace gradient by invariant gradient, so invariant gradient is given by this delta fz is just the usual gradient of f composed pz at 0. So you will see that if you take invariant gradient, then even in dimension 1 things are not nice. Okay, so there is some problem, and there is a way to define invariant or proper or right choice of invariant Dirichlet-type space, which I am not going to discuss in this talk. Here we'll only focus on Euclidean Dirichlet-type space. So that is why we are just calling it Dirichlet-type space. So let's now see the formal definition of Dirichlet-type space. Okay, so here also for the timing, I have included both PI, this invariant Poisson kernel, as well as Euclidean Poisson kernel, but eventually we'll only focus on this Dirichlet-type space or Euclidean Dirichlet-type space. So it is the collection of all functions in the Hardy space of the ball. So it can be seen as a reproducing kernel Hilbert space associated with the reproducing kernel 1 upon 1 minus inner product ZW to the power D. And we impose the condition that the grad f should be square integrable with respect to the measure P mu Z dvz, where P denotes the volume measure. And this is over the open unit ball. And it turns out that it's a closed subspace of Hardy space. So it's a Hilbert space in its own right. And it contains all the polynomials. You can easily see that because you will see that this polynomials extends continuously on the boundary, and you can just bound them by some constant, and integral of the Poisson integral turns out to be just 1. So that is how you get the fact that d mu, the Dirichlet-type space, contains all complex polynomials in Z1, Z2, Z. Now this second property which I stated here, that here I stated only for Euclidean Poisson kernel, that the monomials are mutually orthogonal if and only if mu is rotation invariant. So here T stands for the torus. So it's if the measure is rotation invariant, then only you'll get monomials to be orthogonal. And the proof of this is not direct. We'll need another fact which we are going to see later. So let me just state this, and let's move to the. I hope I'm not going too fast. So yeah. So let me now move to the next slide. Yeah. So there are a few more facts, because just now we noticed that Dirichlet-type space is Hilbert space. So it turns out to be a reproducing kernel Hilbert space. And we have to impose this norm. So there is a factor 1 over t which is necessary for some uh, for further calculations, and so you can easily see that every z is a bounded point evaluation, because same is true for Hardy space. So here also you'll get the same uh, observation. And this kernel, because since it's a reproducing kernel Hilbert space, there is a kernel which is holomorphic in Z and anti-holomorphic in W in the second variable defined on ball cross ball, satisfies the identity that kz0 is constant function 1. And that can be seen here, because if you notice, then you'll see that this if you take any function here such that f of 0 is 0, then it is orthogonal to constant. Okay, so this is what we need. And with these facts, now we can, because it's a now Hilbert space of holomorphic functions, so there are some natural obvious questions. First is, you can, because as I said, polynomials are there, so z, it contains z1 z2 zd, and you can multiply this. If you can look at multiplication by z1 as a linear transformation on the subspace of polynomials. Okay, so it's a linear transformation defined on the subspace of polynomials in Dirichlet-type space. Now the question is that whether this multiplication by z1 extends boundedly to the entire Dirichlet-type space. Okay, or equivalently, can we say that you take any f in the Dirichlet-type space d mu, whether z1 times f is also in the Dirichlet-type space? And this we can ask for z2, z3, and zd. Okay, so all zj. So this is the first natural question which comes to any operator theorist, that you can whether the multiplication by zj is a bounded operator from Dirichlet-type space to Dirichlet-type space. Now, second question is that, because we notice that it contains polynomials, so the question is that whether polynomials are dense in d mu. Okay, so both the questions in totality are not known. Okay, except the case d equal to 1, which is obtained by Richter. In case d is bigger than or equal to 2, there are some partial known cases, and which we'll see in the upcoming slides. So in d equal to 1, this is obtained by Richter, and I have included the references. There are two papers, one appeared in Crele in 88 and one in Transactions of AMS in 91. And see, you can easily notice while reading the Richter's paper, his arguments are heavily relying on one variable theory. Okay, so now, and the arguments cannot be easily modified to push the results in several variables. So one really needs to find a different way to look at these problems, and this is what we are going to. However, now you will see that there is a different approach, but again, this approach may have some limitations, and that is why you could not get complete answers to these questions. But let's see how we can. Okay, so to discuss this approach, let me. So this is, if you notice, if you look at the Richter's papers, then one of the key observations in his arguments, it's one identity, and it's very surprising that he has not stated this identity in the form of a theorem. It's there implicitly in either in proof or in the discussion. So this now one can try to generalize this identity to several variables, and after working out many examples, especially you can work out the examples where monomials are orthogonal, or there are some examples where you can take measure to be non-rotation invariant, and there using various identities you can figure out that this is the right formulation. And this formulation looks a bit complicated, but it's not like that. So if you look at the left hand side, it's the summation over all tuples of integers gamma, d tuples of integers gamma, such that, so suppose gamma you denote by gamma 1, gamma 2, gamma d, and the modulus of gamma is just summation of gamma 1, gamma 2, gamma d. So you are taking the left sum on the left hand side over all gamma, which are integers, positive non-negative integers, such that gamma 1 2 plus gamma 1 plus gamma 2 plus gamma d is equal to k, where k is some fixed positive integer. And so you can think of this as spherical sum, and in one variable the sum disappears, and what you get is just inner product z gamma p inner product z gamma q. So in one variable summation disappears, in multivariable there is a sum, and you can think of this as spherical sum, which appears in multinomial theorem, for instance. And the left hand side depends on k is an integer. The right hand side also depends on k, but now you can see that there is a linear polynomial in k. So you'll get the right hand side is of the form a plus b times k. So you can think of the right hand side as a linear polynomial in k, okay. And that is somehow related to the notions of higher order isometries, which we may discuss if time permits. So this identity looks simple. So let me discuss another observation. Suppose you assume that monomials are orthogonal, okay. So here what you can, because see this identity holds for all p and k, p and q, okay. So you can make the right hand side vanish easily, and you can also make the first term on the right hand side also, the left hand side vanish and first term on the right hand side vanish, and then you can work out, you'll see that the monomials are orthogonal will imply that monomials are orthogonal in L2 of d mu, okay. So L2 of mu, if monomial are, but if monomials are orthogonal in L2 of mu, then this mu has to be, this is over unit sphere, so mu has to be necessarily rotation invariant, okay. And so you can also prove that if mu is rotation invariant, then monomials are orthogonal in Dirichlet-type space. So this identity can be used to prove the fact which I stated earlier. And let me now discuss some consequences of this identity in one variable. Okay, now you'll see that this identity, although it's algebraic in a sense, you are talking only about polynomials and finite sum. There is integral, so it's not completely algebraic, but nevertheless it will allow you to show that when z is a multiplier in Dirichlet-type space in dimension 1, okay. So here here's the argument. So now what you do, you start with a polynomial. So basically we have to show that it's a multiplication by z, it's a bounded transformation. So you write p of z as z times q of z plus p of 0, and you look at the difference between the norm of zp and norm of p, okay. Here we can write, because of this, as I said, in dimension d equal to 1 the sum disappears. So this difference is nothing but the L2 mu norm of p square, of course, you have to take. Now p, we know that it can be written in the form zq plus p of 0. So you can easily see that, and this integral, you can see that this L2 mu norm is over unit sphere. So you'll see that you can write it, you can dominate this by 2 times the L2 mu norm of q square plus the constant p of 0 modulus square will appear, and the total density of the measure, which is mu of circle. So here now it's unit circle. Again, we can use this identity, because now we know that there is identity that this q norm of L2 mu can be written as the difference of this, but this minus term you can ignore, because here you will get this will be a non-negative. So you just retain norm p square, and the second term is as it is. But now this constant p of 0, we know that it's a bounded point relation. So 0 is a bounded point relation. So you can see that this you can dominate it by the Dirichlet-type norm, and so this will give you 2 times 1 plus this. So it's some constant times p norm. Now you can take this on the right hand side, and you can dominate the norm of zp by some constant times norm of p. Okay, so this proves. Okay, now to extend this, because we have now estimate on a subspace of polynomials. If you assume the density of polynomials, then you get the fact that z is a multiplier. Okay, and there is another way. In one variable, one can prove density of polynomials independently, which we'll discuss later. Again, that can be seen through this multivariable argument, but not this Richter's identity is not sufficient here. Here you have to assume somehow uh, density of polynomials. So certainly this provides a different approach than given by Richter, and somehow this algebraic identity can be used to address these issues. So it's natural to think that this algebraic identity may have some consequences in several variables also. And you'll see that yes, you can answer the earlier questions in some special cases using this identity. Before I move to the next slide, I just want to, because this was the first point, that this Richter's identity fails for invariant Dirichlet-type space.
Samir?
Yeah.
Yeah, this below norm, you have calculated the below the remark.
Yeah.
The norm coming from the d mu, right?
Yeah. It's actually here I have not written, but this norm of ZP is Dirichlet-type norm.
Okay, Dirichlet.
So it's the same norm. So here I have used this d mu. Here I didn't, because it's one variable, and again the calculation was becoming clumsy. So, but it's a Dirichlet-type norm. So okay, this is the estimate of norm, means estimate in Dirichlet-type norm. Yeah, yeah, you are right. Okay, so here again let me say this again, that this invariant Dirichlet-type space, in case of this Dirichlet-type space, this identity fails. Okay, and there is a way to define right notion of invariant Dirichlet-type space, which we will not discuss here anyway, but yeah, let me now move to the next slide. Now here is you can, because although we cannot answer the question whether each zk is a multiplier of d mu, you can formulate this. Okay, and so basically you are starting with the problem and you are trying to formulate in equivalent statements, and with the hope that those equivalent statements may be more tractable. So or maybe easy to verify. So the first condition or first statement is equivalent to the existence of constant c. So that now you can see that this is interesting condition, that here you are taking the weighted volume measure or norm of f in the weighted volume measure, with weight being Poisson integral. And here actually this p should be pe. So now onwards, here onwards, we are only talking about Euclidean Poisson kernel, Euclidean Poisson integral. So this will be pe, and this should be dominated by the norm of d mu, the norm of f in d mu, square, and this condition is or you can see that this estimate has a particular name in the literature. So they so this, and it has been studied very well. So they call it, if you look at the weighted volume measure with weight being the Poisson integral, then it's a correlation measure for the Dirichlet-type space. So this has been studied for classical Dirichlet-type space, Berman space, and so many known function spaces. So I'm not saying that this is easy to check, okay? However, you'll see that there are instances in which these conditions can be checked with less effort. Okay. And there is third equivalent statement, which is known for one variable Dirichlet type space. And this is basically you take supremum over R is varying between 0 and 1, and the integral is over sphere, and then you compute this norm of f of R with respect to this weighted surface area measure. So you can, yeah, so so what I want to say is that this both the conditions, they may be easier in some instances, but you cannot say that they are, means we are essentially we are solving the problem. Okay, so we are just bypassing the problem, and only thing is that there is a hope that if we get this estimate, then we may be able to get boundedness of the multiplier. So to show utility of this theorem, I will just discuss one case. Again, this is not completely satisfactory, but let me discuss the corollary. So now you take the measure mu to be a weighted surface area measure, and you assume that the weight is a bounded measurable function. So if you take a bounded measurable function and you look at the weighted surface area measure, then one can, this is not difficult, one can verify this estimate, okay, because you can just dominate, and I think I'm not going to get into those calculations, but one can verify this estimate. Yeah.
Sorry to interrupt you. There is a question from Professor Ajit Iqbal Singh.
Okay, yeah.
Is the space d mu invariant under the decomposition of by Mobius map?
Okay, so I do not know the answer, but okay, yeah, I do not know the answer, but I have, so there are some observations in that direction. So for instance, if you look at the invariant under the, if you look at the invariance of the inner product under the unitary group, then what you get is just the measure has to be necessarily the surface area measure. So I don't think that, because see, the reason is that once the measure is rotation invariant, okay, so because now here she's talking about Mobius group, I understand correctly, if I understand correctly.
Yes,
okay?
Yes, Mobius group.
So if the space is invariant under even rotation, then the measure has to be rotation invariant. But in general, there are plenty of measures which are not rotation invariant. So in general, we cannot hope that the answer is affirmative.
Okay.
Yeah. Actually, see, this is not a one space, but it's a collection of, because you can start with any positive Borel finite measure, and you can associate the Poisson integral, Poisson kernel, Poisson integral, and then you can consider the respective Dirichlet-type space. So in general, we cannot hope that it has. This is true for the classical Dirichlet-type space on the.
You mean 1 over inner product ZW logarithm?
Yeah. But here the space, as I said, that monomials need not be orthogonal. So certainly such symmetry is not these spaces may not have this symmetry. Okay, so let me come back to this corollary. So here the only thing which is bothering is the assumption, means again here we are trying to answer the question whether Zj is a multiplier for weighted surface area measure. Okay, now measurability you cannot avoid, but boundedness certainly uh, one may try to remove this condition, but at least from our earlier characterization we are unable to remove boundedness, and even we do not know whether Zj is necessarily a multiplier for Dirichlet-type space in dimension bigger than equal to 2. Okay, so we do not have example of a measure for which Zj is not multiplier for the respective Dirichlet-type space. Uh, there are plenty of examples you can generate now with this corollary. However, the general problem seems to be quite uh, quite far from our reach. Okay, and once you get multiplier, then it is natural that you can define the multiplication. So here there is a typo mzj. You can define the multiplication tuple mz, mzj1, mzd, and now the natural thing is that what can you say about this tuple? So we have already noticed that in Richter's identity, this the spherical moments, means whatever there was on the left hand side, they have a polynomial growth, in fact a growth of linear polynomial. And one example which fits into the scheme is two variable Dirichlet shift. If you take d bigger than equal to 3, then that this Dirichlet shift in variables bigger than equal to 3 do not doesn't satisfy Richter's identity. Okay, it satisfies only in case dimension 1 and 2. So let me now let me now come to the next question, which is, because now we address when Zj is a multiplier. Now we want to discuss when polynomials are dense in the Dirichlet-type space. Here also the complete picture is again we do not know when this happens and whether this happens or not. And you'll see that in literature there are simple counter examples where polynomial density fails in many function spaces of holomorphic functions. Here there things could be better, or the polynomial density may be 2 in general, but yeah, one needs to so investigations are needed to know that. So let's so this theorem is a tool to get polynomial density. And let me it looks a bit technical, but it's not. So we just need one notion, which is we call it weighted Dirichlet integral. And so you integrate grad of f with respect to the Poisson integral and times volume measure and over the unit wall. And so this weighted Dirichlet integral, with this Dirichlet integral we can now state the theorem. So the condition is that you take lambda to be any weighted surface area measure with weight being harmonic in a neighborhood of closure of the unit wall. Okay, I'll actually yeah, here you can try to relax this condition. You can replace this weight by just dilations of Poisson integrals. So that also that is also sufficient. And we have these estimates for every polynomial and every r varying between 0 and 1. Okay, so it's a uniform estimate, uniformity in r. Okay, so if you have this estimate, then one can show that this this weighted Dirichlet integral, so d mu of fr minus f tends to 0 as r tends to 1, and one from left hand side, and this F is any element in the Dirichlet-type space. So and from this, because you will see that this FR, because it's holomorphic on a bigger ball, so I should explain what is FR. FR of Z is just F of R times Z, where R is a positive number between 0 and 1. So you will see that this FR is holomorphic in a bigger ball, so it can be approximated by polynomials. So if FR can be approximated by polynomials, F can be approximated by FR. So you will see that this F can be approximated by complex polynomials, and that is to say that polynomials are dense. Okay, and one can verify that this estimate about the weighted Dirichlet integral can be verified in case d equal to 1. Okay, so again, in the case d equal to 1, it's not completely obvious. You need a highly non-trivial result due to Shibori, which was obtained in this Krele in 2001. And so this is what, so one can, in one variable case, or in case d equal to 1, you can compute this d lambda p. And so if you can verify that the matrix 1 minus r to the power k plus 1, k plus l, AKL is defined using, so these are the terms precisely coming in d lambda p, and you can easily see that there is a this expression suggests you to look at the positive semi-definiteness, and if you can verify that this is positive semi-definite, then you will get this estimate. Okay, and so that is how you can conclude, you can get polynomial density. So one way to attack this problem is that you try to reduce this inequality or this estimate to positive semi-definiteness of certain matrix. Now you have to move to several variables, which appears to be a difficult task, but there is a chance that you may get plenty of measures where you can ensure polynomial density in Dirichlet-type space. So this is more or less the state of function theory pertaining to Dirichlet-type space, and you can. So now I hope I have some time. Let me take few minutes to explain the motivation and how it started. So it started with the work of Jim Agler. Now this is the paper American Journal of Mathematics in 1990, and then this Agler's notion was generalized to several variables by Gleason and Richter in integral equation operator theory in 2006, and their motivation was Dury-Arvesson shift. Okay, so they introduced this notion in more generality, but here let me discuss only joint 2 isometry. And joint isometry is easy to understand. So basically you have to look at, if you write qt of x to be summation tj star x tj, and if qt evaluated at identity, so you'll get summation tj star tj. If it is equal to identity, then you get the notion of joint isometry, and it's a very natural thing to generalize this to joint 2 isometry. You basically you look at I minus 2 qti plus qt square I equal to 0, and there are plenty of examples. As I said, Dury-Arvesson 2 shift is one of the examples which is joint 2 isometry, but it's not joint isometry. And once you do see in operator theory, once you define a class of tuples or operators, the natural question is what is can you classify? Okay, and in one variable you can write down this condition easily. It is just I minus 2 t star t plus t star square t square equal to 0, and somehow you'll notice that this condition is equivalent to the polynomial growth of the moments. So by moments I understand the function from set of non-negative integers, say k, into t star k tk. So these are the moments, k going to t star k tk, and if these moments they have polynomial growth, then you land up in classes of operators similar to this 2 isometry. So linear polynomial corresponds to 2 isometry, and if you take arbitrary polynomial, then you get so-called M isometries. And there you replace now this moments k going to t star k tk by just q t to the power k, then you get spherical moments and you can define similar tuples. Okay, there is I don't think this is a great deal, but now the classification, it's in one variable. The complete classification is due to Richter, and what he has shown that if you add some more adjectives like cyclicity and completely non-unitary, then you can show that any 2 isometry with these 2 properties is necessarily multiplication by z on Dirichlet-type space. Okay. So that's a complete classification, and so which I stated here, that any cyclic completely non-unitary 2 isometry. Completely non-unitary means it doesn't have unitary direct summand. Okay. And it has to be necessarily multiplication by z on Dirichlet-type space for some positive finite positive Borel measure on the unit circle, and it so there are more conditions, like because now this d mu is a model space, so one can again ask whether the polynomials are dense. So the answer is yes, polynomials are always dense. And you can again refresh this into operator theoretic term, which is wandering subspace property. I'm not going to get into that. However, you get some idea about this, and so now I'll just discuss another slide and then we'll stop. So because I think this is very important example, and this is a paper by Bhattacharjee, I think with Jaydev, Dinesh, and Ishmael, I think if I'm correct, in linear algebra and applications in 2017. I think this is a very interesting paper, and what they have constructed a class of examples where this polynomial density or wandering subspace property fails. Okay, and the argument is it's very powerful in the sense that you look at the subspace, you take any nice Hilbert space of holomorphic function, you look at the subspace HA for which f of a equal to 0. Now, if it has wandering subspace property, then you will see that the zero set of this HA has to be necessarily the zero set of the wandering subspace. But wandering subspace is a subspace of Hilbert space of holomorphic function. So suppose it is generated by some holomorphic function, then in many examples you can show that it is singly generated, and then it is a zero set of a holomorphic function. But zero set of HA has to be singleton A, because this is how you define HA. So singleton A cannot be equal to the zero set of a holomorphic function in several variables, and that's a contradiction. So because zeros are not isolated, if you in several variables, variables are more than one, and so now these examples may suggest that in Dirichlet-type spaces also polynomial density may not hold in for all measures. Okay, so we do not know. So again, this Richter's model theorem also fails in for commuting tuples, d tuples for d bigger than 1. And the simple example, you take the one variable Dirichlet-type space and you look at d square root by 2, d square root by 2. Now you'll see that this in the tuple, both the components, they depend on each other. So you cannot model by multiplication by z1, z2, because z1 and z2, they have to be linearly independent. So there are several difficulties. However, it could be a reasonable question that what are the cyclic joint 2 isometries which can be modeled as multiplication by z on Euclidean Dirichlet-type spaces. Okay, so I think that this is a more reasonable question, and yeah, we hope to come back to these issues in future. So I think I would like to, so there are some partial results, but I'm not now getting into that, and I'll maybe we'll keep some time for discussion. So I stop here. Thank you very much. You may ask questions if you have.
Yeah, thank you so much, Samir.
Hmm.
If anyone has question, you may ask.
Yeah, Surjit and Samir.
Yes, yes.
Yeah, this is Galadhar. I
Ah,
I think the obvious questions beyond what you have done are clear, but for emphasis, I must say that the multi-connected situation involving the Dirichlet operator
ah,
definitely needs further investigation. Of course, the two isometry part is no
ah,
longer present because I don't think there will be isometries or questions about isometries.
yeah.
But along the lines of the work of Abrahams and Douglas, where they found operators, in fact, families of operators analogous to the isometry by looking at Hardy spaces on multi-connected domains. Uh,
Okay, okay. Ah,
very, very interesting to see what the Poisson integrals and kernels would be.
ah, ah.
Standard ones have been, of course, discussed, but if you bring in a measure and you try to make up Dirichlet-like spaces, what they
Okay,
are
okay.
and what the properties would be like
Ah,
is certainly worth considering.
yeah, 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 yeah.
Of course, beyond the ball, there are other domains in the multivariate context where the Poisson kernel particularly has been studied in detail by Korani in all kinds of situations, single domains and bounded symmetric domains and so on and so forth. But that again is for the classical Poisson kernel, whereas looking at it as a family perhaps hasn't been initiated at all. And the analogous question about, I mean, it's not even clear what would be a two isometry.
Yeah, 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 yeah.
Oh, I mean, that definition needs to be made, first of all, right?
Yes, yes.
In this context, of course, I mean, Amir has some of the, I mean, he had this recent preprint about what he calls kata isometries and so on and so forth. That's worth looking at and
Yes, yes.
possible generalizations. Okay.
Yeah, yeah, I agree because see this, yeah, means because whenever there are isometries, there could be a natural generalization uh, of two isometry or M isometry associated with various domains. Here actually, I have because I have recently because this is for many means young operator theorists or function theorists. See this, I have seen recently a paper where I think it is possibly by if I'm sure I'm not sure, or maybe Brett Wick. So they have done something related. So it's a function theory on Hartog's triangle, Hartog's domain. So I think possibly it's right time to go beyond classical domains and try to investigate its connections with operator theory, or maybe yeah, yeah, yeah. Thank you very much.
Connected domains in particular, I
Ha,
think
ha.
are a very interesting set of examples.
Okay, okay, okay. I'll certainly look at yeah,
Right.
yeah, those. Ha. So I think this is the old paper of Abrams with Douglas, I guess.
Yeah, yeah.
Ha, ha,
Abrahams
ha.
and Nicholas. Yeah, right.
Yeah, yeah.
Right. Okay.
Yeah. Thank you very much.
Can I say something?
Yes, yes, please, ma'am.
I wrote in the chat already, but you yourself are saying it is right time to look at other domains. So
Yeah.
what I wrote is, so I'm speaking also. You know, there is old paper by Fustenberg on Poisson kernels,
Okay.
where group is replaced by a Lie group, and then homogeneous spaces, and then the unit circle is replaced by a set called boundary, and
Okay.
that has earned the name of Fustenberg boundary.
Oh, acha, acha, okay, okay. I
Okay,
didn't know.
but his paper is called Poisson kernels only. Fustenberg's paper.
Okay,
So
okay.
I can tell you the reference properly after.
No, no, I'll search.
looking at
I'll
this.
search. I'll search.
So
Yeah.
you look at the literature on Furstenberg boundaries,
Yeah.
and you will they will all refer to Furstenberg's paper. He called it by Poisson kernels.
Okay. Thank you.
Okay.
Thank you very much. Yes.
And since you yourself are saying I'm interrupting.
No. It is all right. So
Okay.
I'm also learning. I'm also trying to
Very, very
understand.
good
Yes.
talk. Thank you.
Thank you. Thank you very
I
much.
wrote in the chat also.
Okay. Thank you very much, ma'am. How are you?
I'm fine, thank you.
Oh, yeah. Good to see you.
For me too, I learned. I'm the learner.
Yeah.
Any more question from audience? Okay, if not, then from this point I will hand over to Srijan.